It seems extremely appropriate at the end of week 3 that we would start to consider the Earth's overall atmospheric circulation, which really is a direct result of these various pressure and density and flow situations that are associated with differential heating and changes in density, changes in pressure that we've been seeing and learning about in these animations this week. We could easily create an experiment that creates convection. I very much encourage you to do this, is to get a container that we put some water in, a clear container that we can visualize the flow in it easily. Add carefully some water at the bottom that would be colored. You could do that with an eyedropper if you're careful, and gradually fill up the container. And then we would heat the left-hand side of this particular container, and we could add, say, a colored ice cube at the other end. And if you let this simulation take place and you observe it, you'll see that the circulation pattern is almost instantly formed, that you'll get a circulating flow with the warmed air being heated on the left-hand side and the cool air, or the cooled water in this case, being descending on the right-hand side, and it produces this circulation convective cell within the water. This cell structure is very characteristic of differential heating, and in fact occurs quite quickly, and is great significance to the Earth as a whole. In fact, it was noted that there are 3 primary circulation cells for the Earth as a whole, and this was noted around 1850 or so, when William Ferrel, through some systematic observations, recognized that there were 3 primary circulation cells in each hemisphere, I should say. We have the Hadley cell, the polar cell, and the Ferrel cell, and we'll see these in more detail. In fact, convective cells, whether large or small, are formed almost continually whenever there's differential heating. If you light a candle flame in gravity, you'll get a convective cell being formed locally, and that actually replenishes the oxygen for the flame and allows it to burn brightly. If there were no gravity, if you try to light a candle in space, a very poor and anemic candle flame is formed, because there is no convection without gravity. For the cells to be large and persistent, though, there has to be prolonged heating. And so larger systems associated with the scale of the Earth require persistent differential heating. Smaller cells are formed in day and night situations between land and water. And these are, of course, what we're going to be seeing are generalizations. The Earth itself is an extraordinarily complex place with lots of things going on. So here are our 3 cells that we were talking about: a Hadley cell, a Ferrel cell, and a polar cell. And those are associated with these different flows. The Hadley cell causes this circulation really at the tropical regions, where the equatorial heating produces a warming, and that warming starts drawing in warmed moist air from the surrounding area. Warming produces cooling, and one of the characteristics of the Hadley cell is in fact the formation of a cloud band around the Earth, as we'll see. The polar cell occurs in the northern part and the southern part of the Earth, at the poles, in other words, or near the poles, and it's associated really with intense cooling that takes place in the most northerly and southerly parts of the Earth, and that produces a descent, and then we produce a relative warming that takes place. Obviously not as warm as the tropics, but relative to the polar air, it's warm, and we get another cell that's formed in this mid-latitude area, this Ferrel cell. It's probably the least well formed of this overall system. It tends to be a bit parasitical, that it draws its energy from the other cells to a certain extent, and it's also strongly mixed by various other processes. Note that this picture that we're showing, or this sketch, is extraordinarily distorted. The Earth's atmosphere is an incredibly thin layer. It is extremely vulnerable to change as a result of its thinness. Overall, this tropopause that we're referring to here is only about 12 kilometers deep, which is a distance that one can walk easily in a morning. That is very different from the characteristic horizontal distances that are associated with the Earth as we experience it as humans. The atmosphere is truly a thin geometric component, and that geometric component again plays a big role. This Hadley cell again produces this equatorial flow at the surface and a counter-equatorial flow at higher elevations. Associated with this cooling as the air rises is typically a formation of clouds, and that formation of clouds actually accentuates the convective cell because it produces a different kind of heating as well. So we get that overall effect as well. It's about 30 degrees of latitude that the cell stretches over in both hemispheres, and there's a relative low pressure typically that's formed around the equatorial band, and a relative high pressure where the air descends, which plays a significant role. You might ask yourself why these winds are curved, why they're not just straight north and south, and that's a direct association with the Earth's rotation, that bend occurs for that, and we'll learn more about that in a later week. But that is something that we can see here. There's always a bend of these flows to the right from its normal direction in the northern hemisphere, and a bend to the left in the southern hemisphere, producing characteristic winds from the northeast and southeast in the tropical region. The doldrums, this area where these flows come together, produce no strong net north or south flow, and that lack of that south and northerly flow produces this characteristic region called the doldrums, where ships sometimes experience extraordinarily calm weather. And this band where these flows come together is called this intertropical convergence zone. And if you look at satellite photographs, particularly over the Pacific, you'll frequently see a band of clouds that's visible there, showing where the air is rising. The polar cell is the one that's formed near the axis of the Earth's rotation, and that's often associated with intense cooling that takes place as a result of very low incoming radiation from the sun, and it moves back in the circulation pattern again, covering roughly 30 degrees latitude, but that of course is a variable amount depending on specific conditions on the Earth. There is a relative warming that takes place as we move further south, and that produces a warm air rise around 60 degrees north and south latitude, and creates this persistent high pressure situation over the poles, and a very stable situation, as we'll see, over the polar regions. These flows again are bent by the Coriolis, or by the Earth's rotation, and it causes this shift from a pure north-south wind to one that shifts again to the right in the northern hemisphere and to the left in the southern hemisphere. The Ferrel cell is this mid-latitude cell, and it's the one that sort of connects up the Hadley cells to the polar cells. Often what happens in the mid-latitude region is a kind of a battle between polar air that's picked up characteristics of the areas of the Earth that get less intense radiation, and the tropical regions, and there's a lot of mixing and a lot of confusion and complexity in this area. And so this Ferrel cell is often the least well formed or least obvious of the cells that are formed. But it does play a role in these mid-latitude cells and mid-latitude weather. It's less stable, less well-formed, but it can be viewed at times as being a fairly characteristic pattern. The air flowing poleward is deflected to the east by Coriolis, again by this rotational effect, and it results in westerlies in this part of the Earth, and we get that persistent flow that comes from the south and the west, producing winds that were quite important for the navigation of the Earth in the earlier stages of the Earth's exploration. The horse latitudes is that convergence area that takes place with the descending air from the Hadley cell, where the Ferrel cell picks this up. And again, this is a relative area of calm winds, where there's less persistent winds to the north and south. And sailors that used to go through this, story is told, used to sometimes have to dump some of their cargo in order to be able to get through this so that they wouldn't run out of food. They, of course, didn't have refrigeration, or some of the advantages of modern life. And they are sometimes told that they even dumped their horses overboard rather than being caught in the horse latitudes for some periods of time. And we get those two characteristic belts of relatively low flows or low winds that take place in those mid-latitudes area. Generally high pressure, generally subsiding air, but again remember that the real picture is much more complex. But this is not surprising that this descending air, which is warmed as it descends and produces this downward flow, produces that drying effect, that the air that is already had its moisture dropped, particularly the intertropical convergence zone, and as a result, the Earth's largest deserts are often formed right at the area of the horse latitudes. And one can see that very clearly, that the horse latitudes are strongly associated with the Sahara desert system and with a number of the desert systems that occur in South America, North America, and the Australia continent is strongly influenced by the effect of this descending air that's associated with this strong Hadley cell that's formed in the tropics. Even in South Africa, we have a tendency towards very strong drying effects that take place at that, and that's true in Asia as well. So these two subtropical pressure belts play an extraordinarily big role, and it's again a direct evidence of this role of convection, the role of differential heating. You may ask yourself, why are there three cells formed? Why not just one big one? And it turns out that the answer to that is a little bit more complex, but is quite fascinating as well. It's probably beyond our scope in our course, but the essential characteristic is because of this rotating effect, because of this bend. If there were just one cell, the bend would only be in one direction, and this would produce a net drag on the Earth, which would tend to change the rotation of the Earth, but that would cause the winds to accelerate. And that interaction between the Earth's rotation and the drag forces causes this to break down into the first possible stable configuration, and that first possible stable configuration is for there to be three cells present. The two-cell solution is not possible as well. It would be possible to have a 5-cell system or a 7-cell system, but the first stable one is the 3-cell system, and that's the one that is fairly characteristic of the Earth. If you want to learn more about this, there's lots of information online. I very much encourage you to dig in and to keep up your curiosity. Next week, we want to then look at the specific ways that these things occur in the ocean and tie in the ocean system to the overall atmospheric system.